At the turn of the 20th century, the world was standing on the edge of a scientific transformation. The air of Europe was filled with the hum of invention and discovery. Steam engines powered cities, electricity illuminated streets, and new theories promised to unlock the very structure of the universe. Humanity believed it was on the verge of understanding everything. The elegant equations of Isaac Newton and the precise laws of James Clerk Maxwell painted a universe that was ordered, predictable, and mechanical, a clockwork reality governed by reason and mathematics. For centuries, this classical view of physics had shaped every aspect of science. According to it, if you knew the position and motion of every particle, you could predict the future with absolute certainty. It was a comforting thought, a universe that behaved like a perfectly designed machine, with every gear turning in harmony. But beneath this comforting illusion, nature was hiding secrets that refused to fit into these neat equations. In the late 1800s, physicists began to notice tiny discrepancies, small cracks in the foundation of classical physics. These were not large enough to alarm the scientific world at first, but they were persistent, and they refused to go away. Among them was a strange problem related to light and heat, known as blackbody radiation. It was a puzzle that would lead to one of the greatest revolutions in human thought. A blackbody is a perfect absorber and emitter of radiation. When heated, it glows, first red, then orange, then white, and eventually blue as the temperature rises. Classical physics, however, could not explain how the intensity of this emitted radiation changed with temperature and wavelength. According to classical theories, as the wavelength of light shortened, the energy emitted should increase infinitely, a result known as the ultraviolet catastrophe. But experiments proved otherwise. The real data showed that energy peaked at certain wavelengths and then dropped sharply. The classical model had failed. In laboratories across Europe, scientists struggled to reconcile this paradox. Some blamed experimental error, others thought the theory needed minor adjustment. But one man, a quiet, deeply thoughtful physicist named Max Planck, decided to confront the problem directly. Working at the University of Berlin in the year 1900, Planck did not set out to change the world. In fact, he was known for his conservative belief in classical physics. Yet destiny had chosen him to ignite a revolution. Planck approached the blackbody problem with mathematical precision. He tried to fit experimental results using every classical method known, but nothing worked. Then, in a desperate attempt to make sense of the data, he introduced a bold new idea, one that seemed absurd even to him. What if energy was not continuous? What if it was emitted in discrete packets, small chunks of energy? Planck called these packets quanta. In one simple equation, E to F, he expressed something profound. The energy, I of radiation, was proportional to its frequency F, with H representing a new constant, later called Planck's constant. It was the birth of quantum theory. Though Planck himself thought of it as a mathematical trick rather than a description of reality, he had unknowingly opened a door that would change science forever. At first, few realized the significance of what Planck had done. The equation worked, yes, but it was so radical that even Planck hesitated to accept its full meaning. He had implied that the universe, at its core, was not smooth and continuous but quantized, built out of indivisible energy packets. Reality, it seemed, was not a flowing river but a collection of discrete drops. The implications were staggering. If energy could be quantized, then perhaps light, matter, and even time itself could exist in discrete steps. This idea shattered the deterministic universe of Newton and introduced uncertainty, probability, and randomness into the heart of physics. The age of certainty was over. The world of science was slow to react. For many, Planck's theory was a curiosity, not a revolution. But a young patent clerk in Switzerland, Albert Einstein, saw its true potential. In 1905, Einstein used Planck's quantum idea to explain another mystery, the photoelectric effect, why light could knock electrons off metal surfaces. According to classical theory, light waves should gradually transfer energy to electrons, but experiments showed that electrons were ejected instantly when light above a certain frequency struck them. Einstein proposed that light itself was made of quanta, tiny particles later called photons, each carrying a fixed amount of energy determined by Planck's equation. The stronger the frequency, the greater the energy of each photon. This simple yet profound idea changed everything. Light, once thought to be a continuous wave, also behaved like a particle. The dual nature of light had been discovered, and the foundations of quantum physics began to form. This was more than a scientific discovery, it was a philosophical earthquake. For centuries, reality had been seen as something solid, predictable, and understandable. Now, it appeared strange, uncertain, and deeply mysterious. Einstein himself later said that Planck's discovery was the most revolutionary act of physics since Newton. Yet even Einstein would struggle to accept the full consequences of the quantum world he helped to reveal. Planck's quanta did not just solve a mathematical problem, they introduced a new way of seeing the universe. The smooth and continuous became discrete and unpredictable. Energy was no longer an endless flow, but a collection of tiny, indivisible amounts. This simple shift would lead to new questions that no one could answer at the time. How do these quanta interact? Why do they exist? What governs their behavior? As the early 20th century progressed, a new generation of scientists took up the challenge. Niels Bohr used quantum ideas to describe the structure of the atom, showing that electrons orbit the nucleus in quantized energy levels. Werner Heisenberg introduced the concept of uncertainty, proving that one could never know both the position and momentum of a particle simultaneously. Erwin Schrödinger developed wave equations to describe the probabilities of where particles might exist. All these discoveries trace their origin to the moment Max Planck introduced his constant. That tiny h became the symbol of a new universe, a universe governed not by certainty, but by possibility. The birth of the quantum revolution was not a sudden explosion, but a quiet awakening. It began in the dim glow of laboratory lamps, with scientists trying to understand why heated objects emit light the way they do. Yet from that small question arose an entire new vision of reality. Imagine for a moment the courage it took to challenge centuries of belief. Planck was not a radical thinker. He believed in order, in laws, in the elegance of classical physics. Yet, when faced with evidence that defied tradition, he chose truth over comfort. That decision marks the true beginning of the quantum revolution, not just a change in equations, but a change in mindset. It was the moment when science admitted that nature was deeper, stranger, and more complex than anyone had imagined. By 1910, the word quantum had become a whisper among physicists. Some dismissed it as an odd mathematical curiosity. Others felt it pointed to something fundamental about reality. But what no one realized then was that this single idea would one day lead to technologies that define the modern world: lasers, semiconductors, computers, and quantum mechanics itself. In the beginning there was resistance. Many senior physicists refused to accept the implications of quantization. They argued that Planck's idea was only temporary, a tool to fix an anomaly. Even Planck himself struggled to believe that energy could truly be quantized. He once said, "I did not seek to found a new branch of physics, I merely wanted to explain a small experimental detail." But as history would show, the universe doesn't bend to human expectation. The evidence kept growing. Every experiment confirmed the strange predictions of quantum theory, and every failure of classical physics pushed the scientific community closer to acceptance. The more scientists looked into the atomic world, the more it defied the old rules. The quantum idea was like a seed, small, fragile, almost invisible, yet destined to grow into a towering tree of knowledge. It would spread its branches across physics, chemistry, and even philosophy, transforming how humanity understands existence itself. In the early years of the 20th century, as Europe marched toward modernity, an invisible revolution was taking place in laboratories and lecture halls. It was a revolution without banners or slogans. One fought with equations, experiments, and imagination. The old order of physics was collapsing, and from its ruins, a new reality was emerging. The birth of the quantum revolution marked the beginning of a journey into the unseen. It was the moment humanity realized that the deeper we look into the universe, the stranger it becomes. Atoms and energy were no longer solid and predictable. They danced in patterns of probability, governed by mysterious laws beyond human intuition. And it all began with a man who dared to question the obvious. Max Planck, sitting before his calculations in 1900, unaware that he had just ignited the spark that would forever change the way we see the universe. The quantum revolution was not born out of ambition or fame, but out of necessity, a response to nature's refusal to fit within human expectations. It was a reminder that truth often hides in the smallest of details, waiting for a mind bold enough to see it. And so, from a problem of blackbody radiation emerged the foundation of quantum mechanics. The language of the microscopic world, the heartbeat of atoms, and the whisper of light itself. This was the birth of a new era, an era where certainty gave way to curiosity, and where the universe revealed itself not as a machine, but as a living mystery. The spark that Max Planck lit in 1900 did not fade. It began to smolder through the corridors of European science. Yet at first it was a quiet fire, seen only by a few curious eyes. For years after his announcement, most physicists continued their work as if nothing had changed. Classical mechanics had been too successful, too comforting to abandon overnight. But in every laboratory, every experiment dealing with light, heat, or atoms, strange results kept whispering the same message: the old physics was dying. As the first decade of the 20th century unfolded, the great minds of the era began to sense that Planck's discovery was more than a clever fix. Something profound was hiding in his tiny constant. Each new observation seemed to strengthen the idea that nature did not behave continuously, but in jumps, quantum leaps. The smooth fabric of reality was, in truth, woven from discrete threads. In 1905, Einstein's paper on the photoelectric effect exploded across the scientific world like a thunderclap. He showed that light itself behaved as if it were made of particles, photons. This was a daring claim. It challenged the sacred belief that light was purely a wave, as proven by countless experiments. For a moment, physics seemed torn between two realities: was light a wave or a particle? Einstein's answer was revolutionary. It was both. The dual nature of light became one of the strangest truths of the new quantum age. This duality did not fit into human intuition. It broke logic. It shattered the comforting certainty that the universe could be described in simple, mechanical terms. Yet the evidence was undeniable. When light struck a metal surface, electrons were released instantly, but only if the light's frequency was above a certain threshold, regardless of its intensity. The brighter the light didn't matter, the color did. The energy was quantized. Planck's constant reappeared, linking Einstein's photons to the very foundation of energy itself. Planck's and Einstein's ideas slowly merged into a single, breathtaking realization: energy and matter were not separate, they were two forms of the same underlying reality. A few years later, Einstein's own theory of relativity would reinforce this unity through his famous equation, E=mc², showing that mass could become energy and energy could become mass. The world was being redrawn, not only by new equations, but by a new philosophy of existence. By the 1910s, quantum thinking began to spread among Europe's brightest minds. In Copenhagen, a young Danish physicist named Niels Bohr was fascinated by atomic structure. The atom, once thought indivisible, had been shown to contain a dense nucleus surrounded by orbiting electrons. But classical physics predicted that these electrons should lose energy and collapse into the nucleus. Yet atoms were stable. Why? Bohr turned to Planck's quantization idea for the answer. He proposed that electrons could occupy only certain fixed energy levels, and that they jumped between them by absorbing or emitting quanta of light. This explained not only the stability of atoms, but also the mysterious patterns in the spectra of hydrogen, the fingerprints of atoms. When an electron jumped down an orbit, It emitted a photon of precise energy. The light from stars, flames, and gases all began to make sense through Bohr's quantized vision. Bohr's atomic model was elegant and beautiful, but it came with unsettling implications. It suggested that at the smallest scales, nature worked in sudden transitions, not smooth motions. Electrons didn't slide between levels, they leapt. The word quantum leap, once poetic, became literal. The birth of quantum mechanics was no longer a mathematical theory, it was a new picture of reality. Still, contradictions haunted the theory. How could something be both wave and particle? How could electrons exist in allowed orbits without violating the laws of motion? Physicists were venturing into territory that defied logic, yet experiments confirmed the bizarre predictions again and again. By the 1920s, the quantum revolution had truly begun to take shape. A generation of daring thinkers emerged, young, restless minds who refused to be bound by old assumptions. Among them was Werner Heisenberg, a brilliant German physicist who in 1925 created a new mathematical framework called matrix mechanics. Heisenberg's work stripped away visual imagery and focused purely on measurable quantities, expressing atomic behavior through abstract mathematics. It was a radical departure, physics without pictures. Around the same time, Erwin Schrödinger, an Austrian physicist, developed wave mechanics, a different but equivalent approach. He imagined electrons not as point particles, but as waves of probability, existing in multiple possible states until observed. His famous Schrödinger equation became one of the cornerstones of quantum theory, describing how these probabilities evolve over time. When Schrödinger's and Heisenberg's ideas were combined, a new and deeper understanding emerged. Matter was not solid, not fixed, but a dynamic cloud of possibilities. At the quantum level, certainty evaporated. The act of observing could influence the outcome itself. This was the dawn of one of the most profound ideas in science, the uncertainty principle, formulated by Heisenberg in 1927. It stated that one cannot know both the position and momentum of a particle precisely at the same time. The more accurately you measure one, the less you can know about the other. This was not a limitation of technology, it was a law of nature. The consequences were staggering. Determinism, the cornerstone of classical physics, was gone. The future was no longer written. Instead of strict predictability, the universe operated on probabilities. The quantum world was not a realm of certainty, but of potential. A place where particles could exist in many states simultaneously, where cause and effect blurred into mystery. For many, this was deeply unsettling. Even Einstein, who had used quantum theory to make his own breakthroughs, resisted this randomness. He famously declared, "God does not play dice with the universe." But Bohr responded gently, "Einstein, stop telling God what to do." Their debates echoed through the decades, shaping the philosophical heart of the quantum revolution. Outside the academic halls, few could grasp the magnitude of what was happening. Yet the world was already beginning to change. The strange rules of the quantum realm soon became the foundation of all modern technology. The discovery of the photoelectric effect led to solar cells and light sensors. The understanding of atomic structure enabled chemistry to advance into new materials and medicines. Later, transistors, lasers, and computers all emerged from quantum principles. The revolution that began as an attempt to explain blackbody radiation had reached into every aspect of human life. It transformed our industries, our communication, our medicine, and even our philosophy. The microcosm, once invisible and irrelevant, became the engine of the modern world. But the story of the quantum revolution was not just about technology. It was about a profound shift in how humanity sees itself. Classical physics had painted a universe where everything followed exact laws, where if one could measure everything, one could predict everything. Quantum mechanics destroyed that illusion. It taught us that nature is not a passive machine, but an unpredictable, creative process. Observation and reality were intertwined. The observer was no longer separate from the observed. This realization carried immense philosophical weight. It hinted that consciousness itself might play a role in shaping what is real. Some physicists resisted this idea, others embraced it, but all agreed on one thing: reality at its core was no longer objective and static. It was dynamic, probabilistic, and deeply connected. As decades passed, the implications of this revolution continued to unfold. Quantum mechanics gave rise to quantum field theory, uniting particles and forces under one elegant mathematical framework. It explained why the sun shines, how atoms bind together, and how energy transforms into matter. It became the foundation of particle physics, leading to the discovery of quarks, leptons, and the mysterious Higgs boson. And yet, despite its overwhelming success, quantum mechanics remains a paradox. It is the most accurate theory ever devised. Every prediction it makes has been confirmed with astonishing precision. Yet its interpretation still puzzles the human mind. What is a wave function? What happens when a quantum system is observed? Does reality collapse into one outcome? Or do all possibilities exist simultaneously in parallel worlds? These questions continue to haunt scientists and philosophers alike. The birth of the quantum revolution was not just a scientific milestone, it was a turning point in human consciousness. It forced us to abandon the comfort of certainty and embrace the beauty of mystery. It showed that truth is not always logical, that reality is far stranger and more profound than imagination. Max Planck once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it." His words proved prophetic. The generation that followed him, Einstein, Bohr, Heisenberg, Schrödinger, Dirac, and others, built an entirely new world upon his constant H. Today, every laser beam, every smartphone, every computer chip is a quiet tribute to that moment in 1900 when Planck first dared to think differently. The spark he created has become the foundation of modern civilization. But perhaps the most remarkable legacy of the quantum revolution lies not in technology, but in perspective. It reminds us that the universe is not something to be conquered or fully known, it is something to be continually discovered. Each mystery solved opens 1,000 new ones. The quantum world humbles us, forcing us to accept that knowledge will always come with uncertainty. And that uncertainty is not a flaw, but a feature of existence itself. Even now, over a century later, the quantum frontier continues to expand. Scientists are building quantum computers that exploit superposition and entanglement to perform calculations beyond the reach of any classical machine. Researchers are exploring quantum teleportation, quantum cryptography, and the strange phenomenon of entanglement, where two particles remain mysteriously connected across vast distances. What Einstein once called spooky action at a distance is now a tool for the next revolution in communication. And yet, at the heart of all these modern marvels lies the same simple idea: energy comes in quanta. That humble equation, E to F, still governs the smallest dances of nature. It whispers through the glow of a light bulb, the pulse of a laser, the orbit of an electron. It reminds us that even the most ordinary light that reaches our eyes carries within it the fingerprints of the quantum revolution. The story that began with Max Planck is far from over. It continues in every experiment probing the boundaries of quantum gravity, in every attempt to unify quantum mechanics with general relativity, and in every mind that dares to ask the question, why? The birth of the quantum revolution changed not only science but the very spirit of human curiosity. It taught us that progress begins when we question the obvious, when we look deeper into the patterns we take for granted, and when we have the courage to admit that the universe is stranger than our logic can bear. In the end, the quantum revolution is not just about particles or equations. It is about the human drive to understand the unknown. It is a story of doubt transformed into discovery, of mystery turned into meaning. From the glow of Planck's furnace to the circuitry of modern computers, the same invisible law flows through time. That energy, matter, and even reality itself are quantized. The revolution that began in silence now echoes through every corner of existence. And as we look into the night sky, at the stars radiating across billions of years, we see the same quantum light that first puzzled Planck more than a century ago. It is a reminder that every photon that reaches our eyes carries with it the history of that revolution, a story of how one man's curiosity changed reality forever. The birth of the quantum revolution was not an end but a beginning. The moment humanity stepped beyond the visible and dared to explore the invisible. It was the moment we realized that the universe is not a simple machine, but a living mystery, waiting to be understood, one quantum at a time. At the end of the 19th century, the world of science seemed complete. The giants of classical physics, Newton, Maxwell, and Galileo, had built a foundation so strong that most physicists believed only minor details remained to be solved. The laws of motion, the nature of gravity, and the equations of electromagnetism appeared to describe everything from the motion of planets to the behavior of light. The universe seemed orderly, mechanical, and entirely predictable. To many, physics had reached its final chapter. Lord Kelvin, one of the most respected scientists of the age, famously declared that physics was almost finished, except for two small clouds that hung on the horizon. Those clouds, unnoticed by most, would soon unleash a storm that would tear apart the very framework of science. They were small problems, but they would become the seeds of the quantum revolution. The first cloud was the failure to explain the motion of light through the mysterious ether, an invisible medium once believed to fill all of space. The second was the inexplicable behavior of radiant energy emitted from heated objects, the blackbody radiation problem. These puzzles seemed insignificant at first, yet behind them lay the cracks in a system that had ruled for centuries. Classical physics was based on a simple principle: determinism. Everything in nature could be predicted if one knew its initial conditions. If you knew where a planet was and how fast it was moving, you could calculate its entire future. It was a comforting belief. The idea of a universe governed by absolute laws. Laplace, the great French mathematician, once imagined an intelligence that could see all particles in the universe at once. To such a mind, nothing would be uncertain. The future and past would be equally clear. But nature, it turned out, had other plans. As scientists looked closer at the hidden world of atoms, the predictions of classical physics began to fail. The more precisely they measured, the more contradictions they found. The universe that had once seemed so perfect began to look incomplete, even fragile. The first great challenge came from James Clerk Maxwell's equations of electromagnetism. These equations described how electric and magnetic fields moved and interacted, and they worked beautifully for large-scale phenomena like light waves and radio signals. But when physicists tried to apply them to the microscopic world of atoms, inconsistencies began to appear. For example, according to classical theory, an electron orbiting a nucleus should continuously radiate energy as it moves, causing it to spiral inward until it crashes into the nucleus. If this were true, atoms could not exist, yet matter clearly did. Something fundamental was missing. At the same time, experiments on heat radiation produced results that classical equations could not explain. When a metal object was heated, it glowed in predictable colors. First red, then orange, then white, then blue as it became hotter. But classical theory predicted that at higher frequencies, the intensity of radiation should increase without limit, an impossible result. This became known as the ultraviolet catastrophe. The name itself carried drama, catastrophe, and indeed, it was catastrophic for classical physics. For centuries, scientists had believed that the laws of nature applied smoothly and continuously to everything, from the smallest atom to the largest star. But now, this assumption was breaking down. Every attempt to fix the equations failed. The numbers simply refused to align with experiment. It was as though nature was mocking human understanding. Something strange was happening at the atomic level, something that the elegant mathematics of Newton and Maxwell could not touch. Into this confusion stepped Max Planck, a man deeply devoted to the classical tradition. Planck was not a revolutionary by nature. He admired order, logic, and certainty. Yet fate had chosen him to become the destroyer of the very ideas he loved most. Planck began by studying the energy emitted from heated objects, what scientists called blackbody radiation. He tried every known equation to fit the experimental data, but none worked. Finally, in desperation, he introduced a radical assumption that energy was not continuous, but came in discrete packets, quanta. This simple assumption solved the problem perfectly. The data aligned. The catastrophe disappeared. But in doing so, Planck had opened a Pandora's box. If energy came in quanta, then the fundamental principles of classical physics, continuity, determinism, and smooth motion, were no longer universal truths. Planck himself did not immediately grasp the magnitude of his discovery. He thought of his idea as a mathematical convenience, not a statement about reality. Yet the consequences of his work would shake the world of physics to its core. The smooth, predictable universe of Newton was beginning to dissolve into something uncertain, fragmented, and deeply mysterious. The challenge to classical physics had begun. Only 5 years later, in 1905, Albert Einstein, then a young patent clerk in Bern, published a paper that would push Planck's idea even further. Einstein was fascinated by the photoelectric effect, a strange phenomenon in which light shining on a metal surface could eject electrons. Classical theory said that increasing the light's intensity should increase the energy of the emitted electrons. But experiments showed otherwise. The energy depended only on the color or frequency of the light, not its brightness. Einstein proposed a daring explanation. Light, he said, was not a continuous wave, but a stream of discrete particles, or photons, each carrying a quantum of energy proportional to its frequency. This was a direct challenge to the classical view of light as a wave. The wave theory had explained reflection, refraction, and interference perfectly. But it could not explain the photoelectric effect. Einstein's theory united two conflicting pictures, wave and particle. It suggested that light could behave as both, depending on how it was observed. This duality defied logic and intuition. How could something be both a wave that spreads through space and a particle that strikes a single electron? The world of classical physics was built on absolutes. Waves were waves, particles were particles. The new quantum ideas blurred that boundary, introducing a universe where certainty no longer existed. Even as Einstein's ideas spread, another classical assumption was beginning to crumble: the concept of the ether. For centuries, scientists believed that light waves must travel through some medium, just as sound waves move through air. This invisible substance, called the luminiferous ether, was thought to fill all of space. But when Michelson and Morley performed their famous experiment in 1887 to detect Earth's motion through the ether, they found nothing. The speed of light was constant, regardless of direction. The ether did not exist. This discovery, combined with Einstein's theory of relativity, demolished the last pillars of classical certainty. Space and time, once considered absolute, were now relative to the observer. The classical idea of an objective clockwork universe was gone. By the early 1910s, physics was in crisis. The old framework could no longer explain the behavior of light, matter, or even gravity. The most trusted equations failed at the smallest scales. Nature was no longer behaving like a predictable machine. It was revealing patterns of probability, chance, and duality. To many, this was terrifying. To others, exhilarating. A few visionary minds began to sense that a new order was emerging from the chaos. Among them was Niels Bohr, who combined Planck's quantization and Einstein's light quanta into a model of the atom. Bohr proposed that electrons orbit the nucleus in fixed energy levels, and that light is emitted when they jump between these levels. It was a brilliant synthesis, and another nail in the coffin of classical physics. In Bohr's model, the atom was not governed by the continuous laws of Newtonian motion. It operated by rules that defied reason. Electrons could only occupy specific orbits, nothing in between. They did not gradually move from one orbit to another, but leaped instantaneously. emitting or absorbing a quantum of light. This was the new reality, abrupt, discontinuous, unpredictable. The old world of classical certainty was gone, and with it, the comfort of knowing that the universe was fully understandable. The new physics was filled with paradoxes. Light could behave as both wave and particle. Electrons could jump without traveling, and energy, once thought to flow smoothly, existed in discrete steps. The challenge to classical physics was complete. The foundations that had supported science for centuries were cracking, revealing a deeper, stranger world beneath. But revolutions do not happen in silence. The early quantum pioneers faced immense resistance. Many senior scientists dismissed these new ideas as mathematical tricks or philosophical nonsense. Even Planck and Einstein struggled to accept the full implications of their discoveries. Planck, ever cautious, refused to believe that energy quantization was a fundamental property of nature. Einstein, though he expanded the idea, later rejected the notion that chance governed the universe. Both men found themselves standing between two worlds, the classical and the quantum, uncertain where reality truly lay. Yet the evidence kept growing. Each new experiment confirmed what the equations predicted. The photoelectric effect, atomic spectra, and heat radiation all pointed in one direction, toward a quantum world. The challenge to classical physics was no longer a question, it was a fact. The universe was not continuous, not deterministic, not predictable. It was governed by probabilities, by jumps, by uncertainty. And so, the great transformation began, a journey from the known into the unknown, from the comfort of certainty into the mystery of the quantum realm. The 19th century had given humanity the illusion of mastery, a universe ruled by logic and control. The 20th century shattered that illusion. Planck's quanta, Einstein's photons, Bohr's orbits, each discovery tore another piece from the fabric of classical thought, revealing a deeper layer of reality. The challenge to classical physics was not just a scientific struggle, it was a philosophical awakening. It forced humankind to confront a profound truth that knowledge has limits, that nature's deepest secrets cannot always be captured by human logic. The age of the clockwork universe was over. The age of uncertainty had begun. As the dawn of the 20th century crept across the scientific world, an unsettling truth began to emerge. The foundation upon which all physics had been built was starting to crack. The great monuments of Newtonian mechanics and Maxwell's electrodynamics had reigned unchallenged for centuries, explaining the motion of planets, the fall of an apple, and the behavior of light waves. Scientists believed they stood at the summit of knowledge, ready to refine the final details of the universe's grand design. But deep within the heart of matter, in the unseen world of atoms and energy, strange anomalies were whispering a different story. The cracks first appeared in the study of something as simple as light emitted by heated objects. When metal was heated, it glowed red, then orange, then white. Physicists called this phenomenon blackbody radiation. Classical theories tried to explain this glow by assuming that energy could vary continuously, much like the flow of water. Yet every attempt to apply known laws failed miserably. As scientists calculated the radiation of higher frequencies, their equations spiraled into nonsense, predicting infinite energy emissions, an absurd result known as the ultraviolet catastrophe. Nature, clearly, refused to obey the rules humanity had written for it. This catastrophe wasn't merely a mathematical problem, it was a crisis of understanding. For decades, physicists had relied on determinism, the comforting belief that every cause had a predictable effect. The universe was like a clock, its gears turning with perfect precision. But these glowing experiments, these strange behaviors of heat and light, seemed to suggest something else entirely. Something hidden beneath the surface of classical laws. The old framework that once explained the stars could no longer describe the tiny flickers of energy inside atoms. It was Max Planck who finally dared to step into the unknown. In 1900, working tirelessly to understand the blackbody problem, Planck proposed a radical idea. What if energy didn't flow smoothly? What if, instead, it came in small, indivisible packets? He called them quanta. This idea shattered centuries of belief. It meant that energy was not infinite, not continuous, but limited to specific steps, a staircase, not a ramp. Planck himself didn't realize the enormity of what he had done. He saw it as a temporary fix, a mathematical trick to make the equations work. Yet that trick became the spark that ignited the quantum revolution. Planck's formula matched experimental data perfectly. For the first time, the spectral distribution of blackbody radiation made sense. The infinite energies vanished, replaced by finite, logical results. It was as if the universe had been speaking in riddles, and Planck had finally found the key. But this new key didn't fit comfortably into the lock of classical physics. It suggested a world governed not by continuous motion, but by discrete, jump-like transitions. The elegant determinism of Newton began to crumble before the chaotic whispers of the quantum world. Soon after, another mystery rose to challenge the old order: the photoelectric effect. When light hit a metal surface, it ejected electrons, but in a way no classical theory could explain. According to Maxwell's wave theory, increasing the brightness of light should increase the energy of the emitted electrons. But experiments revealed something completely different. The energy of the ejected electrons depended on the frequency of light, not its brightness. Even the faintest beam of high-frequency light could knock electrons free, while an intense red beam did nothing. It made no sense, unless light, too, behaved like particles. Albert Einstein stepped into this puzzle with a bold interpretation. Building on Planck's idea, he proposed that light itself was made up of quanta, discrete packets of energy, which we now call photons. This was heresy to many physicists at the time. Light had long been understood as a wave, proven by countless experiments of diffraction and interference. To claim it also behaved as a particle defied logic. Yet Einstein's explanation fit perfectly with the photoelectric observations. It was undeniable. Reality was not what it seemed. Each new discovery deepened the crisis. The atomic model itself, long thought to resemble miniature solar systems with electrons orbiting nuclei like planets, began to fall apart. Classical physics predicted that orbiting electrons should lose energy, spiral inward, and collapse into the nucleus within microseconds. But atoms were clearly stable. The old laws couldn't explain why. Something invisible, something profoundly different, was at play inside the atom. In 1913, Niels Bohr attempted to patch the gap. He adopted Planck's idea of quantization and applied it to the atom. Bohr proposed that electrons could orbit only in certain allowed energy levels and could jump between these levels by absorbing or emitting specific amounts of energy. It was a bold synthesis, merging the old and new into a model that could finally explain atomic spectra, the mysterious fingerprints of elements. When hydrogen's spectral lines matched Bohr's predictions, the scientific world gasped. For the first time, quantization wasn't just an abstract idea, it was real, visible, and measurable. Yet even Bohr's success couldn't restore the stability of classical thinking. Every advance in understanding the microscopic world only widened the gulf between the old and new physics. Electrons didn't behave like miniature planets, they flickered and vanished, existing as both waves and particles, depending on how they were observed. Subatomic particles ignored the clean boundaries of logic, breaking rules that had guided physics for centuries. Determinism, once sacred, was replaced by probability. Reality, it seemed, was woven not from certainty but from chance. The deeper physicists looked, the stranger it became. Experiments like the double-slit test showed that electrons could interfere with themselves, acting like waves when unobserved and collapsing into particles when measured. Observation itself appeared to shape reality. The old idea of an objective universe, one that existed independently of human measurement, began to fade. The observer had entered the equation. For scientists who had grown up under Newton's shadow, this was disorienting. The laws of classical mechanics had offered clarity and confidence. They had built engines, predicted planetary orbits, and powered the Industrial Revolution. Yet now, at the smallest scales, nature refused to follow those rules. Instead, it danced to rhythms that were unpredictable and probabilistic. What was once a world of clear causes and effects now dissolved into a mist of uncertainty. Still, out of this chaos came profound beauty. The challenge to classical physics was not a destruction but a rebirth, a transformation of thought. It revealed that the universe was far more dynamic and mysterious than anyone had imagined. The rules that governed apples and planets did not hold for electrons and photons. Two worlds coexisted, one classical, predictable and familiar, the other quantum, uncertain and strange, and both were equally real. As the 1920s unfolded, young physicists embraced the new paradigm with enthusiasm. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac carried Planck's and Einstein's ideas further, building a new mathematical framework for quantum mechanics. Heisenberg's uncertainty principle declared that certain pairs of properties, like position and momentum, could never be known precisely at the same time. This wasn't a flaw in measurement, it was a fundamental truth of nature. Schrödinger's wave equation described particles as waves of probability, not solid objects. Dirac's equations later united quantum theory with relativity, revealing even deeper layers of reality. Together, their work cemented the downfall of classical physics at the microscopic scale. The universe was no longer a predictable clockwork, but a sea of probabilities, a realm where cause and effect blurred into possibilities. Yet far from chaos, this new understanding birthed a revolution of technology and imagination. Quantum theory explained chemical bonding, superconductivity, and the behavior of semiconductors. It laid the groundwork for lasers, transistors, and the computers that now define our world. The challenge to classical physics had not merely rewritten equations, it had rewritten the story of reality. Humanity discovered that beneath the familiar laws of motion lies a hidden order. A quantum world that defies human intuition yet governs everything around us. It is a realm where energy leaps in quanta, particles blur into waves, and the act of observation shapes existence itself. When we look back, we see that this challenge was never about breaking the old, it was about expanding our vision. Newton's laws still describe the orbits of planets, just as Maxwell's equations still guide the behavior of light in our macroscopic world. But beyond those boundaries lies a deeper truth, a universe built on uncertainty, harmony, and endless possibility. The fall of classical certainty gave rise to a new kind of wonder, one that reminds us that knowledge is never complete, and truth is never static. The quantum revolution taught humankind that reality is more than what we see. It is a vast, shimmering field of probabilities, alive with mystery and meaning. And it all began when a few brave minds dared to challenge the unshakable faith in classical physics and look deeper into the hidden heart of creation. In the twilight of the 19th century, when science stood proud upon the shoulders of Newton and Maxwell, there emerged a man whose quiet determination would rewrite the rules of existence. He was not a flamboyant figure seeking fame or glory. He was a thinker of profound patience and precision. Max Planck, the man whose equation would ignite the most revolutionary transformation in the history of physics. To the outside world, he was simply another German physicist immersed in complex mathematics, but within his mind stirred a question that would shake the very foundation of reality itself. Planck lived in an era when science was celebrated as the language of certainty. Every phenomenon, from the orbit of planets to the flicker of candlelight, was thought to obey a perfect mathematical order. The universe was a clockwork machine, predictable and absolute, yet beneath this harmony, there lingered a puzzle no one could solve, the mystery of how energy was distributed when objects were heated. This simple question, this seemingly small imperfection in the laws of physics, became the riddle that consumed Planck's mind. He was fascinated by light, heat, and the way materials glowed when heated. When metal turned red, orange, then white, scientists could measure the colors and intensities, but no existing formula could describe them accurately. Classical theories failed disastrously. The Rayleigh-Jeans law, for instance, predicted that as the frequency of light increased, the emitted energy would skyrocket to infinity, a result that defied both logic and observation. This paradox was famously called the ultraviolet catastrophe, and it became a thorn in the side of 19th-century physics. Planck, a deeply thoughtful and somewhat conservative man, was reluctant to abandon classical theory. He revered the works of Newton and Maxwell, and he believed that any deviation from their principles must be a temporary imperfection in human understanding. Yet his calculations repeatedly told him otherwise. The data from blackbody radiation experiments simply refused to fit the predictions of classical equations. Something was wrong, profoundly wrong, with the assumptions underlying all of physics. In his search for truth, Planck turned to the mathematics of probability, a field that was gaining new importance in thermodynamics. He drew inspiration from Ludwig Boltzmann's statistical approach to entropy, though he found its implications philosophically troubling. The idea that physical systems were governed by chance rather than strict determinism felt almost sacrilegious to him. Planck believed in order, in laws that governed everything with precision. Yet as he struggled to reconcile theory with experiment, he began to realize that probability might be the key to understanding energy itself. For years, Planck labored over equations, testing every possible relationship between energy, frequency, and temperature. Then, in October of 1900, he made a decision that would change history. He introduced a simple but radical assumption: energy is not continuous but comes in discrete packets. Each packet, or quantum, is proportional to the frequency of radiation. He expressed this in an equation that would forever bear his name, E, where E is the energy of a quantum, once anew is the frequency of radiation, and h is a new constant, now known as Planck's constant. This constant, though small beyond imagination, carried within it the seed of a new universe. It was the scale at which classical laws ceased to function, the boundary where the familiar world dissolved into the quantum realm. For Planck, it was not an act of rebellion against classical physics, but a reluctant step into the unknown. He viewed his quantum hypothesis as a mathematical convenience, a trick to make the equations align with experimental results. But the universe knew better. When Planck presented his findings to the German Physical Society on December 14, 1900, few realized they were witnessing the birth of a new era. His equation perfectly described blackbody radiation across all frequencies, eliminating the ultraviolet catastrophe and matching real data with astonishing accuracy. What began as a patch in the fabric of classical physics turned out to be the thread that unraveled it entirely. Yet even Planck himself resisted the philosophical consequences of his discovery. He did not fully grasp that his energy quanta represented a fundamental property of nature. To him, it was an abstraction, a temporary model that might later be explained in classical terms. He could not have imagined that his small equation would open the door to a universe where certainty dissolved into probability, where particles behaved like waves, and where observation itself shaped reality. Still, history had changed. Planck's constant, that mysterious h, became the cornerstone of a new physics, a language capable of describing the microscopic world. The quantum revolution had begun, though its founder did not yet recognize the revolution he had unleashed. Planck's genius lay not only in his mathematical insight, but in his unwavering devotion to truth. He once said, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it." This quiet humility defined him. He was not a man of ego or sensationalism. His brilliance was matched by a deep moral integrity, forged in a life filled with both triumph and tragedy. In the years that followed his quantum discovery, Planck continued to refine his work, guiding younger scientists who would carry the torch further than he ever imagined. Among them was Albert Einstein, who in 1905 expanded Planck's concept to explain the photoelectric effect, proposing that light itself was made of discrete particles, photons. It was Einstein who fully recognized the revolutionary implications of Planck's work, declaring that energy quantization was not a mathematical trick but a profound feature of reality. Planck admired Einstein's intellect but approached his conclusions with caution. He accepted the photoelectric explanation reluctantly, holding on to the belief that continuity might one day be restored. Yet the momentum of discovery was unstoppable. Bohr's atomic model, Heisenberg's uncertainty principle, and Schrödinger's wave mechanics all traced their origins back to the quiet spark Planck had ignited. Behind the equation stood not just a scientist, but a philosopher of nature. A man who saw science as a moral pursuit, a quest for harmony between reason and reality. For Planck, the beauty of physics lay not in power or invention, but in truth. He once wrote that, "Science cannot solve the ultimate mystery of nature." And that is because, in the last analysis, we ourselves are part of nature, and therefore part of the mystery we are trying to solve. This deep humility set him apart from many of his contemporaries. He worked not for recognition but for understanding, driven by a spiritual conviction that the universe was ordered and rational. Yet the theory he birthed revealed a cosmos that seemed anything but a realm of uncertainty, duality, and paradox. In a poetic irony, Planck's search for absolute order led him to uncover the fundamental unpredictability of existence. By the 1920s, Planck was recognized worldwide as the father of quantum theory. His once radical constant became the key to countless discoveries, from atomic structure to quantum mechanics. But he never saw himself as a revolutionary. He viewed his work as a bridge between the classical past and the quantum future, connecting two worlds with one simple equation. To him, It was not an end, but a beginning, a symbol of the eternal dialogue between certainty and mystery. As he grew older, Planck watched the scientific landscape he had helped shape transform beyond his imagination. The young quantum pioneers who followed him, Bohr, Einstein, Schrödinger, Heisenberg, Dirac, built an entirely new framework of thought. They embraced the strangeness he had hesitated to accept, diving headlong into a world where probability ruled and observation changed outcomes. Though he did not fully agree with all their interpretations, Planck supported their courage and intellect, understanding that progress often required the very boldness he himself had once resisted. His life was marked by quiet tragedy as well as scientific glory. During the turmoil of the early 20th century, Planck endured personal losses that would have broken most men. Two of his daughters died young, and his beloved son Erwin was executed by the Nazi regime for participating in a plot against Hitler. Through it all, Planck remained steadfast in his faith in truth and humanity. Even in the darkest years, he continued to teach, write, and inspire others, believing that knowledge and reason were lights that no tyranny could extinguish. When he passed away in 1947, the world mourned not only a great scientist, but a moral giant, a man whose intellect had transformed physics, and whose integrity had uplifted the human spirit. His constant, H, remains one of the most fundamental quantities in nature, appearing in every equation that describes the quantum world. It is the rhythm of the cosmos, the scale of creation, the whisper of the universe's smallest vibrations. And so, from one man's humble search for understanding came a revolution that continues to define our modern age. The genius behind the equation did not seek fame, nor did he crave recognition. He sought only truth, and in doing so, he uncovered a deeper layer of reality than any before him. His work did not merely challenge the boundaries of physics, it redefined the very meaning of knowledge. Through Planck, the world learned that the universe is not a machine of certainty, but a symphony of probability, and that even the smallest constant can hold infinite wonder. As the 20th century unfolded, Max Planck's name began to echo across scientific halls, whispered not as a mere physicist, but as the man who had unknowingly torn open the veil of reality. His discovery of energy quanta had set in motion a chain of events that would forever alter humanity's relationship with the universe. Yet, even as the world hailed him as a revolutionary, Planck himself stood apart, calm, introspective, and often uncertain about the magnitude of what he had unleashed. He had not set out to destroy classical physics, he had sought only to understand it more deeply. But sometimes, in seeking truth, one ends up rebuilding the world itself. The early reaction to Planck's idea was cautious. Many scientists admired the accuracy of his equations, but doubted the physical meaning of quanta. They saw it as an elegant mathematical trick rather than a fundamental truth. Planck, too, shared that caution. He had faith in the continuity of nature, the belief that energy flowed smoothly, not in discrete leaps. Yet reality had spoken otherwise, and even if he struggled to accept it, the facts were undeniable. It was Einstein who first grasped the full depth of Planck's insight. In 1905, he took Planck's constant and gave it life, proposing that light itself was made of quanta, photons. The photoelectric effect, which had baffled scientists for years, suddenly made perfect sense. Einstein's bold interpretation was radical, suggesting that light, long known to behave as a wave, could also act like a stream of particles. This duality defied common sense and shook the foundations of physics even further. While Planck respected Einstein's genius, he hesitated to follow him into such speculative territory. For Planck, energy quanta were a mathematical necessity, not a description of physical reality. But history was already moving beyond him. By the 1910s, young physicists were diving into the implications of quantization. Niels Bohr, inspired by Planck and Einstein, constructed his revolutionary model of the atom, an image of electrons orbiting the nucleus in quantized shells, leaping between energy levels with flashes of light. Each jump released or absorbed a photon whose energy corresponded to Planck's equation. It was a magnificent synthesis of theory and observation. When the predicted hydrogen spectral lines matched perfectly with experimental data, Bohr's model transformed from speculation into triumph. The quantum had become more than a symbol, it was a fact of nature. Planck watched these developments with a blend of pride and wonder. His once humble constant had become the heartbeat of a new physics, yet he remained philosophical, even cautious, in his interpretations. To him, science was not about conquering mystery, but about humbly approaching it. He saw the growing excitement around quantum theory as both exhilarating and unsettling. It was thrilling to witness the power of ideas he had seeded, but it also meant watching the old, deterministic world he had loved dissolve into uncertainty. As the next generation of physicists rose, Planck found himself both mentor and observer. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac began to craft a mathematical framework that transcended even Bohr's vision. Heisenberg's matrix mechanics and Schrödinger's wave mechanics revealed that particles were not solid points moving through space, but probability patterns, waves of potential existence. Planck's constant, h, appeared in every corner of these equations, linking them to the original insight he had proposed decades earlier. It was as though his constant had become the key to reality's code, the smallest heartbeat of the cosmos, defining how matter and energy behaved at their most fundamental level. As Planck's legacy grew, so too did his reflections on the nature of discovery. He often spoke of the struggle between conviction and curiosity, between what one hopes to be true and what one must accept as truth. For Planck, science was not the pursuit of comfort but of honesty. He believed that truth existed beyond personal belief, beyond human convenience, and that it must be followed wherever it led, even into chaos. Science advances one funeral at a time, he famously said, acknowledging that true progress often required the old ways of thinking to fade away. The genius behind the equation was not measured only by intellect, but by endurance. Planck's life was shaped by the same discipline and perseverance that defined his science. He was meticulous in his work, patient in his reasoning, and guided by a moral compass that never wavered. When Germany was torn apart by war and ideology, Planck remained devoted to his students and to the integrity of science. He spoke of the unity of truth, insisting that knowledge transcended politics and nationality. For him, physics was not just the study of nature, It was a reflection of human character. But fate was cruel to Planck. The tragedies that struck his family could have broken any man. The First World War claimed one of his sons. 2 of his daughters died in childbirth, and in the 1940s, under the shadow of Nazi tyranny, his surviving son Erwin was executed for resisting Hitler's regime. Planck, already in his 80s, faced unimaginable grief, yet even in despair, he never abandoned his belief in the power of reason and truth. He continued to teach, to write, and to inspire. He became a symbol of integrity in an age of darkness, a man who held on to light when the world seemed consumed by madness. Through it all, his creation, that small, mysterious constant, continued to shape the world. By the mid-20th century, the implications of his work had extended far beyond physics. Quantum theory had given birth to entirely new technologies: semiconductors, transistors, lasers, and eventually computers. The digital age that defines modern life traces its roots directly to Planck's equation. Every byte of data, every photon of light in a fiber optic cable, every quantum bit in an emerging quantum computer, all of it carries the signature of that constant, H. Planck did not live to see the full extent of his revolution, but his influence endures in every laboratory, every calculation, and every scientific mind that dares to question reality. His equation remains one of the most profound statements ever written by humanity. A simple line of symbols that encapsulates the dual nature of existence: energy and frequency, matter and light, wave and particle. It is the language of the universe distilled into its most elegant form. To understand the genius behind this equation is to understand more than physics. It is to witness the courage to confront the unknown. Planck's journey was not one of sudden brilliance, but of persistence against confusion. He wrestled with failure, doubt, and paradox, yet he never surrendered to ignorance. His genius lay in his patience, in his willingness to look deeper when others looked away, to question what others accepted, and to find truth even when it defied all expectation. And beyond his intellect was his character. Planck's faith in order and meaning guided him through the storms of both science and life. He believed that the laws of nature were expressions of a deeper harmony, that even in the randomness of the quantum world, there existed an underlying logic waiting to be uncovered. For him, science was not a rebellion against mystery, but a bridge toward understanding it. As he once wrote, "Whence come I and whither go I?" That is the great unfathomable question of life. Science has no answer to it. In those words lies the soul of the man behind the equation, a scientist who understood that knowledge and wonder were inseparable. He had stared into the abyss of the microscopic world and found not chaos, but beauty, an invisible dance of energy and possibility that connected all things. Today, when physicists speak of quantum mechanics, they speak in the language of Planck. His constant defines the scale at which the universe shifts from the predictable to the mysterious. It governs the behavior of atoms, the birth of stars, and even the patterns of radiation left over from the Big Bang. It is the thread that ties together the past and future of the cosmos, linking the smallest vibrations of matter to the grandest movements of galaxies. In every photon that strikes a camera lens, in every spark of energy that powers a computer, Planck's discovery lives on. His genius endures not because of fame, but because of truth. The equation he crafted was more than mathematics. It was a key that unlocked a hidden universe, revealing that reality is not a solid wall of certainty, but a shimmering field of potential. Max Planck began his journey searching for order, and found instead the beautiful unpredictability of existence. His constant reminds us that even the smallest quantities can change everything, that within the tiniest flicker of energy lies the power to reshape human understanding. He never sought to change reality, yet by seeking truth, he did, and so the genius behind the equation stands as a symbol of what science truly is, not the pursuit of control, but the pursuit of comprehension. Not the end of mystery, but its deepening. His legacy whispers through every quantum leap and every beam of light, reminding us that the universe is not made of certainty, but of wonder. The unseen world of particles is a universe beyond the limits of our senses, a place where reality behaves in ways that seem impossible. It is a world where matter dissolves into waves, certainty becomes probability, and observation itself shapes existence. When scientists first peered into this mysterious realm, they discovered that the rules of everyday life no longer applied. Instead of solid, predictable objects, they found a strange dance of particles, moving, colliding, and transforming in ways that defied logic. What they saw was not chaos, but a deeper order, an order hidden beneath the surface of reality. In this invisible universe, particles are the building blocks of everything we see. The stars in the sky, the air we breathe, and even our own bodies. Yet these particles are not tiny solid spheres, they are more like vibrations, bursts of energy existing in multiple states at once. They can act as both waves and particles, depending on how they are observed. This strange dual nature was one of the first great mysteries of quantum physics. Light, once thought to be a continuous wave, also behaved like a stream of tiny packets called photons. Similarly, electrons, which scientists once believed were solid particles, displayed the properties of waves when passed through narrow slits. This wave-particle duality shattered the old certainty of classical physics and opened a door into an entirely new understanding of nature. In the quantum world, the act of measurement changes everything. Before observation, particles exist in a state of superposition. They can be in multiple places, multiple states, even multiple realities simultaneously. But the moment we observe them, this superposition collapses into one outcome. It's as if the universe holds its breath, waiting for us to look, and only then decides what to be. This phenomenon challenged every traditional idea about reality. It suggested that at the most fundamental level, reality is not fixed, it is fluid, uncertain, and shaped by the act of perception itself. This mysterious behavior extends beyond imagination. Quantum entanglement, one of the strangest and most beautiful phenomena in physics, shows that particles can become connected in such a way that the state of one instantly affects the other, no matter how far apart they are. Einstein once called it spooky action at a distance, but experiments proved it real. It is as if the universe communicates in whispers faster than light, binding its particles together in a silent web of connection that transcends space and time. Through the study of this unseen world, scientists began to realize that the universe is far more dynamic and interconnected than we ever imagined. The particles that make up matter are constantly vibrating, interacting, and exchanging energy in an endless cosmic dance. Even the vacuum of space, once thought to be empty, is now understood to be filled with quantum fluctuations, tiny bursts of energy appearing and disappearing in the blink of an eye. Reality, it turns out, is not solid at all. It is a field of probabilities, a vast ocean of invisible energy waves giving rise to everything we see and experience. This revelation has transformed not just science, but philosophy itself. The unseen world of particles reminds us that certainty is an illusion, that what we perceive as reality is only a shadow of deeper, hidden processes. In this mysterious microcosm, cause and effect blur, and time and space lose their rigid boundaries. It is a world that humbles human understanding, yet inspires awe, a realm where nature whispers its deepest secrets through the language of quantum physics. And though invisible to our eyes, this unseen world is the foundation of all existence, proving that the smallest things often hold the greatest mysteries of all. The impact of the quantum revolution on science and technology is one of the most extraordinary transformations in human history. What began as an attempt to understand the behavior of light and atoms has now reshaped the entire modern world. Quantum theory, once dismissed as abstract and uncertain, became the invisible engine driving the age of innovation. Every time we use a computer, make a phone call, or watch a video online, we are witnessing the power of quantum physics in action. The strange and unpredictable behavior of particles at the atomic scale has become the foundation of the technologies that define our daily lives. When scientists first discovered that energy is quantized, They had no idea it would one day revolutionize communication, medicine, and computing. The invention of the transistor, the building block of every modern electronic device, was made possible by quantum mechanics. Transistors control the flow of electrons using quantum principles, allowing the creation of microchips that power everything from smartphones to satellites. Without an understanding of how particles behave in tiny spaces, the digital age would never have begun. Quantum mechanics also gave rise to the laser, a device that uses the precise control of photons to produce concentrated beams of light. Lasers are now used in almost every field, in medical surgeries, data storage, fiber optic communication, barcode scanners, and even in the precision of atomic clocks that guide our GPS systems. These tools of light, born from the mysteries of the quantum world, have illuminated not just our technology, but the very boundaries of human possibility. Beyond electronics and communication, quantum physics transformed our understanding of materials. Superconductors, for example, rely on quantum effects to conduct electricity with zero resistance. This has opened doors to high-speed trains that float on magnetic fields and medical imaging machines that see deep into the human body. Quantum theory even explains the behavior of semiconductors, which made possible the computer revolution and the rise of artificial intelligence. Yet the most astonishing frontier lies ahead: quantum computing. Unlike classical computers that process information in bits of zeros and ones, quantum computers use qubits, which can exist in multiple states at once. This means they can perform complex calculations that would take traditional computers thousands of years. These machines could revolutionize fields such as cryptography, drug discovery, weather forecasting, and artificial intelligence, unlocking solutions to problems that were once thought impossible. The very same principles that once confused Einstein, superposition and entanglement, are now being harnessed to build the computers of the future. Quantum theory has also had a profound impact on our understanding of the universe. It shaped modern chemistry, allowing scientists to map the structure of atoms and molecules. It revolutionized biology through quantum tunneling and photosynthesis research, helping explain how plants convert sunlight into energy with near-perfect efficiency. Even astronomy was transformed, as quantum mechanics became essential to understanding black holes, star formation, and the behavior of matter under extreme conditions. But the influence of the quantum revolution is not only technological, it is philosophical. It forced humanity to accept uncertainty as a fundamental part of nature. It taught us that the universe is not deterministic but probabilistic, not fixed but dynamic. Every discovery in quantum science reminds us that reality is deeper, more intricate, and more interconnected than we ever imagined. The quantum revolution has woven itself into the very fabric of human progress. It has given us the power to manipulate the smallest components of nature and build wonders that previous generations could not even dream of. From the simplest light bulb to the most advanced quantum computer, every innovation is a reflection of humanity's journey into the invisible. What began as a strange theory about the behavior of tiny particles became the blueprint of our modern civilization, proof that even the most mysterious truths of the universe can become the foundation of human advancement. Changing our view of reality was perhaps the most profound consequence of the quantum revolution. Before this transformation, scientists believed the universe was a vast, predictable machine. Every event caused by another in an endless chain of certainty. Isaac Newton's laws had painted a picture of a world ruled by order, precision, and determinism. If you knew all the forces and positions of every particle at one moment, you could, in theory, predict the entire future. But the discovery of quantum mechanics shattered that image forever. The universe, it turned out, was not a clockwork mechanism but a living mystery, fluid, uncertain, and deeply connected. Quantum physics revealed that reality at its core is not fixed. It is built on probabilities, not certainties. The tiniest particles do not move in straight, predictable paths but exist in clouds of possibility. They appear and disappear, jump between energy levels, and seem to exist in multiple states at once. This concept of superposition was beyond imagination. How could something be in two places or two conditions simultaneously? Yet, every experiment confirmed it. The universe, at its most fundamental level, does not follow the simple logic of human thought. It dances to a rhythm of probability, guided by invisible mathematical waves known as wave functions. The act of observation itself became a central mystery. In the quantum world, nothing has a definite form until it is measured or observed. Before observation, a particle exists in a superposition, a blur of possibilities. The moment we observe it, the wave function collapses, and one outcome becomes real. This discovery changed not only science but philosophy. It suggested that consciousness, or at least measurement, plays a role in shaping physical reality. The observer and the observed could no longer be separated. Reality, it seemed, was not something that existed independently of us. It was something that responded to our interaction with it. This idea was unsettling, even to the greatest minds of the 20th century. Einstein famously resisted it, saying, "God does not play dice with the universe." But experiments continued to prove that chance and uncertainty are fundamental aspects of nature. The randomness of quantum behavior was not the result of ignorance. It was a built-in feature of reality itself. The universe was not governed by strict determinism, but by probabilities and possibilities. Every atom, every photon, and every quantum event reminded humanity that nature's true laws are far stranger than anyone could have imagined. The quantum revolution also changed how we perceive the relationship between space and time. Through phenomena like entanglement, it became clear that two particles could remain connected across vast distances, instantly reflecting each other's state, as if distance did not exist. This defied classical logic and even challenged the limits of Einstein's relativity. It hinted that at a deeper level, the universe is unified, a single, interconnected whole, where separation is merely an illusion created by our limited perception. This shift in understanding affected every field of human thought. Philosophers began to question the nature of existence. If reality is shaped by observation, what does that mean for human consciousness? If the universe is uncertain, what does that mean for free will? Even artists and writers found inspiration in quantum ideas, exploring themes of ambiguity, paradox, and hidden meaning. Science and philosophy, once divided, were brought together again by the strange truths of the quantum world. At its core, this new view of reality taught humanity humility. It reminded us that our senses and logic, powerful as they are, can only reveal a small portion of existence. Beneath the surface of the visible world lies a universe governed by laws we can barely comprehend, a universe where cause and effect blur, where certainty dissolves, and where mystery reigns supreme. The quantum revolution did not just give us new technologies, it gave us a new perspective on existence itself. It taught us that reality is not static but dynamic, not rigid but flexible, not separate but intertwined. Everything in the cosmos, from the smallest particle to the largest galaxy, is part of a grand, interconnected web of energy and information. This understanding forever changed humanity's relationship with the universe. It reminded us that the more we discover, the more mysterious the world becomes, and that the true nature of reality may always remain just beyond the reach of complete understanding. The legacy that still shapes the future of the quantum revolution is not just a scientific inheritance. It is a continuing story that defines the very direction of human progress. What began over a century ago as a set of abstract ideas about light and energy has now become the foundation of modern civilization. Yet, even as we use the fruits of quantum theory every day, humanity stands only at the edge of understanding its full potential. The pioneers of quantum mechanics, Planck, Einstein, Bohr, Schrödinger, Heisenberg, and others, may have uncovered the rules of the unseen world, but the game itself is still unfolding. Their discoveries reshaped our view of nature, technology, and even philosophy, leaving behind a legacy that continues to expand with every generation of scientists. Today, the quantum revolution has entered a new phase. We are no longer merely observing the mysteries of the subatomic world. We are beginning to control and manipulate them. Quantum computing, quantum communication, and quantum sensing are becoming the pillars of a new technological age. In laboratories around the world, researchers are using entangled particles to send information faster and more securely than ever before. Quantum encryption promises communication systems that cannot be hacked by any conventional means. Quantum computers are being built to solve problems that would take traditional computers millions of years. The principles that once defied common sense are now being engineered into reality, transforming industries, medicine, and even national security. The legacy of the quantum revolution also lies in its power to inspire imagination. It pushed humanity to look beyond visible boundaries and explore the hidden layers of existence. It showed that truth often lies in paradox, that something can be both a wave and a particle, that two things can be connected across infinite space, that reality itself may be probabilistic. This deeper understanding has influenced not only physics but also chemistry, biology, cosmology, and information science. Quantum biology, for instance, now investigates how quantum effects might play a role in photosynthesis, DNA mutations, and even the workings of the human brain. The boundaries between life, energy, and information are dissolving under the lens of quantum understanding. Yet, this legacy is more than technological or scientific, it is philosophical. The quantum revolution forced humankind to confront questions that reach far beyond equations. What is reality? Does the universe exist independently of observation, or do we bring it into being by perceiving it? Is consciousness a byproduct of matter, or is it woven into the fabric of the cosmos itself? These questions continue to guide modern physics and inspire spiritual and intellectual exploration. Quantum theory, though deeply mathematical, also carries a poetic truth that certainty is an illusion, and that the universe is not a static creation but a living process, continuously unfolding. Even as new generations of scientists push deeper into the quantum realm, they stand on the shoulders of the great thinkers who first glimpsed its mysteries. Each experiment, each discovery, each new theory adds another verse to the story that began with Planck's quantum of energy. The Large Hadron Collider, quantum satellites, superconducting circuits, and the race toward quantum supremacy, all are modern expressions of that original spark. The revolution that began in the early 1900s has become the beating heart of 21st century innovation. But perhaps the most enduring part of the quantum legacy is what it tells us about humanity itself. It reminds us that knowledge is never complete, that mystery is not a limitation, but a source of wonder. It shows that even the smallest particle can hold the secret to the greatest truths. Quantum physics has taught us to question reality, to embrace uncertainty, and to see beauty in complexity. It has united science and imagination in a shared pursuit of understanding the unknown. The quantum revolution's legacy is eternal because it continues to evolve. It shapes not just the machines we build, but the way we think, dream, and see the universe. It challenges the next generation to ask deeper questions and to look beyond what is visible. As we move forward into the quantum age, we carry with us the spirit of curiosity that began it all, the spark that changed our understanding of existence and continues to illuminate the path toward the future. The revolution that once began with a single equation now defines the destiny of humankind, reminding us that the universe is not just something to be observed, but something to be explored, questioned, and forever rediscovered.